Hello, everyone. In this video, we will start our discussion and explanation of our first language, which is the pseudocode. In this video, we'll start giving an overview of the language itself, why it was developed in the first place, and then in later videos, we will dig deeper into the syntax of the language and the different part of the language. And as well, we will go over the steps of the different part of the language, why they were added, and why we need them. So what do you mean by pseudocode? A pseudocode basically is an instruction code that is different than that provided by the machine. So when we use the word pseudocode as well, don't confuse it with the current usage of the pseudocode. Currently, pseudocodes are used as a way of writing down, like similar to algorithm or explanation of a program, how we're going to write it down, but it's not an actual coding. In here, we will going to use pseudocode as a primitive programming language to explain the developing or the steps needed in order to develop a language. So the pseudocode, as I said, it's an instruction code, and it has an interpretive subroutine to execute. It's like implementing a virtual computer. It has its own data types and operation, and it's run in top of machine language. So you have the machine language, which is what was usually used by the programmers. It's run in top of that to provide this virtual computer or virtual layer that makes things much easier to the programmers. And you can also view that all programming languages are more like a virtual computer, which providing this high level way of dealing with the computer without having to deal with the machine language. So pseudocode interpreter, we can think, is programming really difficult? Well, think about it. We are now in the 1950s and things are much different than how it is nowadays. So in the 1950s, the machine was like IBM 650. And what we know about it is there was no programming language available at the time for that machine, not even assemblers. There was the memory with only a few thousand words. So think about it in comparison to the memory that we have nowadays. The programs stored and the data stored as well on rotating drum. And instructions included address of next instruction so that rotating drum was under next instruction to execute and no full rotation were wasted. So if you think about it, everything is hard coded. Location of the memory, where the next instruction is going to be. You have to write things in a machine language as well. And that always brought the problem. What if the address of that where you want to put your next instruction was occupied by something else? How are you gonna use the next instruction? So it really was when they developed the language or when they write a program at that time, they really had to think a lot about what is really existing inside the memory, had to think a lot about the hardware itself, how things are actually working in the hardware. So in that case, you can see that it has a rotating drum, and they had to think about how fast the rotating drum goes and where they're going to be the location of the next instruction so that they can tell the current instruction where to go next. So it's really not as it or how we program nowadays, where you just go ahead and write down the program without having to think too much about the details about the hardware itself and what is actually happening there and how the hardware is organized. So it's much different than nowadays. And to even put things into perspective, this is part of an IBM 650 program. So you see, you specify the location of if you go to the first line here, you have the location of that instruction, the operation, the data, and then the location of the next instruction afterwards. And everything is written down in numbers and in machine language. So as you can see that it's really not that easy to write down things and keep track of how the program would run. So in order to reduce the complexity of that, they started to develop something called program design notations, which is like a control flow diagram that we use nowadays, and which is basically the flow charts. It's very similar to the flow chart. It helped the programmers remember instruction codes, and you can think about similar to assembly language nowadays. However, it were more designed to help the programmers not to be interpreted by programs. Like think about it, or not to be interpreted by computers. So think about it that way, as if you're drawing things, thinking about the sequence of instructions, drawing a diagram, thinking how things are going to move from one phase to the other. So all to help you think about your instruction, about your program, but whatever you draw cannot be used or interpreted by the computer. So that was one first step, but it's still not making things too much easier for the programmer. Other issues that was common at that time as well is floating point arithmetics. So floating point arithmetics was actually not there in the hardware. It was first introduced in the IBM 704, but before that time, it had to be simulated. The hardware itself did not support floating point arithmetics. So they had to do manual scaling, multiply the numbers by constant factor, and they had to use integer processor, manually scale it back, and then in order to get back the floating point operation. So you can see that could be a lot of errors that could happen from that operation. It was not that easy until it was finally introduced in the hardware part by the IBM 704. And to give you an example about how the machine looked like at the time, this is the IBM 650, and this is on the right side, the IBM 704 operator's console. So they are very large and complex and very bulky, and at that time, they were very expensive. You can actually maybe think about it like millions of dollars nowadays. And at first, IBM thought that the only people for this that only about 50 people are gonna need to buy those machines, but they were actually purchased a lot, and they needed to produce even more machines like these ones. So there was a huge demand for those machines, and more programmers start to program those machines. So there was a need to have things being done in a much easier way than how it have been done before using machine learning, using the machine language. Another issue as well that existed in the older machine is indexing. So one of the most common data structure that was used is arrays. And indexing was not available as a feature in the hardware. And how it was done at the time, again, it's more of a simulation done on top of the hardware. So basically, you would add the variable index quantity to a fixed address in order to access the element of an array. And how you would do that, you basically modify the address itself. So you alter the program's own data accessing instructions, and then compute the actual address from pointer, and you add an offset, and then you write it down into instructions data address portion. So you see that you actually modifying the instructions in order to help the instructions work on the next data point that you have in your array. And again, this is very error-prone process. So it has to be done in another way so that you would reduce the errors, especially, again, it's a very common data structure. A lot of programmers need to use it. And that brings us to pseudocode interpreters. So in order to reduce the errors in the floating point arithmetics and the indexing for using arrays, some subroutines start to be written in order to perform those operations. So like think about it like writing down a piece of code in machine language and then sharing this code with other programmers in order and make it accessible so that programmers don't really have to re-implement this code over and over again. So these subroutines became available to reduce the error in the floating point arithmetics and in the indexing process for arrays. And by having those subroutines, the operation itself of programming is now more simplified because the programmer don't have to think about re-implementing floating point arithmetic or re-implementing indexing. And you can see as well that these subroutines simulated instructions, and those instructions were not provided by the hardware. We know that the hardware does not support floating point arithmetics, and we know as well that the hardware does not support indexing. So since already we started to build subroutines in order to handle certain operations that did not exist or provided by the hardware, So the next logical step then is why to not provide an instruction set like a pseudocode interpreter so that it covers a lot of things, create that layer for programmer and make it much easier for programmer to program the machines rather than working directly with machine language and dealing with all the things and the hassles of addresses and everything. So why not to move forward and finally develop another level of programming languages instead of dealing with machine language? So funny enough, this whole idea appeared in an appendix in a book that was published in 1951 by Wilkes, Wheeler, and Gill. And this book, in Appendix D, it described the idea of pseudocode and interpretive subroutines. And most probably they did not recognize or realize the significance of their work. And so they wanted to provide a simplified programming they wanted to simplify programming by providing an entire new instruction code that was simpler than their own machine codes. So basically, it's a virtual computer, and the pseudocode interpreter implements a virtual computer. It implements a new instruction set. It implements new different types of data structures. Those virtual computers, as I mentioned, they are treated as a higher level. They don't work directly with the hardware. You don't really have, as we have seen before, you don't really have to think about addresses or where you to put your next instruction. You don't really have to think a lot about arithmetic, floating point arithmetic not being implemented in the hardware because those subroutines are provided for you. So it's made things much, much simpler for programmers than using machine language. So it's, in a nutshell, it's abstract away hardware details as you can think about it nowadays, how the language is existing nowadays, abstract a lot of details about the hardware. We don't really have to think about how our hardware is organized or how it looks like when we program in languages like Python or Java or C++. And that brings us to our first programming principle. So as we move forward in our discussion about the different programming languages like pseudocode or Fortran or others, we are going to add one more programming language principle, one at a time as we come across it. So the first principle is the automation principle, which is we want to automate mechanical, tedious, or error-prone activities. We don't want to keep redoing or re-implementing over and over again. We want to have those operations or those functionalities to be automated so we reduce the error. And the second principle, the regularity principle. So regular rules without exceptions are easier to learn, use, describe, and implement. So you want to also create a regularity in the language that you are developing to make it easier to learn, to make it easier to use and describe. So these are the first two programming languages principles that we're going to learn about. And then as we move forward with our other languages, we're going to learn about other programming languages principles as well. Hello, everyone. So in this video, we will continue our discussion about pseudocode, and we'll start our discussion about how to design the language itself and the different part. So we'll walk through the steps about adding the different part to our language. Before, we talked about, in previous video, we talked about why we need to have such a language and the importance of having it, but we didn't cover yet how we can actually go ahead and implement it. So now when we are designing our pseudocode, we have to remember a couple of things. It is the 1950s, and the capability that we want to have our system to have in the 1950s, we want to have our system to have floating point operations. We will want to be able to add, subtract, or divide. We want to be able to do comparisons. We want to have indexing. And if you remember as well, the machines at the time did not provide indexing, so we need to have it similar to the floating point operation. The system and the machines at that time didn't support floating point operation, so we want to have a way to make it easy for the programmers or the coders to go ahead and program the machines. We want to have also transfer of control, and we want to have input and output operations. So these are the main things that we want to be able to do with our pseudocode language. And let's see how we can actually achieve that. But before we can achieve that, we need first to understand the hardware assumption that we have and what type of hardware we have. At that time, you have machines like the IBM 650, and this is the hardware we're going to talk about. And it works with words, and the size of the word is basically 10 decimal digits, and it have one sign. And as well, the memory size itself, the whole memory size is about 2000 byte memory. And how are we going to think about the memory? How are we going to divide it? We are going to have 1000 bytes for the data, and we're going to have 1000 bytes for storing the program itself. So this is basically how our memory looks like, and how the assumption that we're going to use about our hardware when we are designing and building our system, or when we're designing and building our programming language. So let's look at how we can actually design our language. We have one word, and that one word will be enough to specify a 3-operand instruction. We are going to have one part for the operation itself, so we're going to have one digit plus the sign to specify the operation, and that will allow us to support 20 different operations, which will be enough for our language so far. And we're going to have as well for the operands, we're going to have 3 digits, three digits operands, and if you see, each will actually allow us to access the memory location, the data area, and the max number of location it can access is basically 1000 location for the data. So if you remember from the previous slides that we talked about, we have 1000 location for the data, and we have 1000 location for the program itself. So by having such constraints, we are making sure that the programmer cannot access the program locations and rewrite the program locations and treating it as data, because he only can access 1000 location. So we're making it harder to make mistakes in the memory. We're also going to have an orthogonal design, and we're going to talk more about orthogonality, but the whole point is the operations should be more intuitive than machine code. We want to make it easy, and we're going to make use of the sign to give more orthogonality in our operations, and we're going to explain that in more details. Now that brings us to bringing more programming language principle, which is the impossible error principle. What we want to do is we want to make error impossible to commit. And so that it's better to make it impossible to commit rather than trying to detect them after they've been committed. So we're trying to make sure that the errors wouldn't happen. So that's why when we picked the length of the operand to be 3 digits, to make sure that the user or the programmer can only access the data location, which is up to 1000 location, and not by mistake go ahead and access where the programs are going to be stored. And also the fourth principle was the orthogonality principles. Independent functions should be controlled by independent mechanism. Independent function should be controlled by independent mechanism. And we're going to have more examples to understand how the orthogonality is actually achieved. Now, when we want to have an instruction, we want to specify the instruction format. So we can have this format like the operation, then the source 1, source 2 for the operation, and then the destination. So for example, if we want to add 2 numbers, x plus y, and then we want to have the result being stored in the destination z. So basically +1, so the sign and the 1 are going to represent the operation itself. So this is the operation number. The 0, 10 is location. 150 is the second location, so source 1 and source 2, and 200 we are going to save our final destination. So how we want to achieve orthogonality principle here is by giving the subtraction operation, giving it a -1. So it's much easier to remember that +1 is for addition, and then the -1 will basically represent the subtraction operation. So if we add some of the mathematical operations that we want to add, so we want to have addition, subtraction, multiplication. Orthogonal to multiplication is going to be the division. We want to have the power of 2, then the square root will be the opposite one, or the orthogonal operation. So by using +1 representing the addition, -1 representing the subtraction, +2 representing the multiplication, -2 representing the division, +3 representing the powering operation, and then or the squaring of a number, and -3 is basically representing the square root. So it makes it easy to understand what operation we're actually trying to achieve. Now let's see what other operations that we want to add to our language. So we want to be able to do comparisons. And when we do comparison, we also remember that comparison can actually alter the control flow. So for example, if x is less than y, then you want to be able to go to z. So the first two operands we have are representing the data location, and destination is the address basically of the next instruction. If you return back to the format of the instruction, so basically the first two representing the data that we're comparing, and then finally the destination where the next instruction you want to jump to if the comparison was true. Now, let's go ahead and add that to our language so far. So we're going to give them also operation. We have to give them numbers. So the equality, we're going to give them 4. So +4 is equal, -4 is not equal. +5 is greater than or equal, and -5 is less than. Okay, what else do we need in our language? In our language, we want to be able to move one number from one location to another location. We want to be able to do that. One way of doing it is we can think, oh, let's just do an addition operation and add a 0 to an address, but that could be insufficient and could be confusing. So it's better to have an operation that is specifically used in order to move a number from or a value from one location to another location. And we can use the operation, we give it a 0 to represent it. So +0 representing the moving operation. And in that case, we don't need 3 operands. We just need 2, which is the source and the destination. So we're going to use the source and then 3 zeros because it's an empty location. And then we're going to have the destination. So when you see an instruction in the format, we know that this is a move instruction. So let's look at our pseudocode so far. So our pseudocode so far, we have all those operations, 1, 2, 3, 4, 5 operations here representing the different arithmetic operation, and then we're going to add the +0 to represent the move operation. What else we need? We mentioned as well that the current or the existing machine did not allow indexing. So that is one of the reasons we want to have subroutines allowing indexing. So we need to provide a functionality or operation for the programmer to be able to do indexing. So when we have indexing, we need a base address and then the index from the base address. So the base and index, basically, that's going to take up 2 operands. And we have to think, what about the third operand that we have? What do we want to do with that? So we could be using it for save value of indexed element for another operation. So basically, when we have this here, so we want to get x of I and place it into z, or we want to get the x and then place it into y of I. So basically, we are going to use it to bring a value from a location based on an index and then place it into another destination, or basically reading a value from a location and saving it inside our array. Okay, and when you think about here, what those things refer to, the I is the memory location where we actually find the actual value to use as our index. So the I representing that. X is the memory address of the array base in the get operation. And in the second operation we have here, X is the memory address of the item to put into Y of I in the put operation. Okay, so we have to think, you have to understand how the instruction is formatted to understand exactly what is happening inside that instruction. Okay, let's look at how we want to do looping. So that's a frequent operation that you actually do an array. So when you have an array, you frequently loop through the element of the array to do different things, maybe addition, apply something. So what we need in order to loop through array, we want to have an iterative variable, array index I, and we want to have an upper bound, like the end where we want to stop after looping through the array. And we want to have the address of beginning of the loop, which is D. So I is for the array index, N is going to be our upper bound, and D is the address of the beginning of the loop. Okay, and This is a new operation that we want to have. So we're going to add a new number, 7, representing the looping operation. Now, when we think about, if we go back here before going into the abstraction, we can think that the looping operation can be achieved by using the comparison operator that we declared before and by using other arithmetic operators. However, if in order to achieve looping, we have to use the other operation, it's going to be harder to understand the code. And it's better to define one operation for all type of looping so not to create errors, because now you have the looping divided into multiple operations, multiple instructions, making it much harder to follow and much easier to generate errors. So that brings us to the next principle of programming, which is the abstraction principle. Avoid requiring something to be stated more than once. Factor out the recurring pattern. So we always know that with the looping, we're going to do comparison operation beside arithmetic operation. So let's just have one operation that does both instead of having to do both and forgetting something and generating more errors in our code. Okay, let's move forward and see what other operations we want to add. So the program wouldn't make any sense if we just do the operation without being able to read data from inputs and write data to an output. So we really need to be able to read the data from a specific input and write it to an output. So how to do it? We just need only a memory location to read from or write to. We don't really need all the other operands that we have. So we're going to use number 8 to represent a reading. So +8 represents reading. And -8, we're going to use it to printing from a source. So -8 for printing and +8 for reading. And from that, we can have finally our final complete instruction set. You're going to find that in some operations we have here, there is no orthogonal operation that we did. There's no orthogonal instruction that we added. Like for example, number 7 for the looping, we just used +7 to increment and test. We didn't use anything for -7 because there is not this orthogonal operation on top of it that it makes sense to add it here. So we left that number empty. Also with the move, there is no -0, and the same with the stop operation that we add number 9 here. It's we didn't add a -9 for it because there is no orthogonal operation that we want to add. So we're just going to leave it empty for those locations here. And from that, we can end up by having we want to have our program structure. We want to think about it. So we have our initial data values. We're going to have the +9s here. And the goal of the +9s is to be a flag to separate between the initial value, program instructions, and the input value. So basically, you are just separating knowing the border. So when you're reading, you know exactly where the program instructions are from and separating it from the input data or the initial data value. Otherwise, you can have mixed things up. So now we have like the initial structure of our program. We know what operations we want to have. We know how large our memory is and what we can store in that. So next we want to move further with our pseudocode language. Hello, everyone. In this video, we will continue our discussion about our pseudocode. But this time we will talk about the pseudocode interpreter. So in a previous video, we talked about the language itself, how to construct the language, what instructions we have, and how the instructions will look like. Now it is time actually to take the language and provide an interpreter for the language so that the language itself or the program can be executed at the end on our machine. Remember that the main language that the machines understand is the machine language itself. And we are providing a more of a higher level language that it makes it much easier for the programmer to code instead of coding in machine language. So our job now in writing down the interpreter is to get the language and then translate it into the machine language in order to be executed finally by the program. And in order to execute it finally by the machine. So how do we implement the interpreter for our pseudocode program? So we wanted to be able to model the interpreter behavior after manual execution. One thing we are going to do in our video here when we are explaining the interpreter, we're not going to go ahead and write it down in machine language because it's going to be very hard for us to understand, very hard for us to follow up with it. And also, we're not trying to really relive the 1950s. More in this video, we want to go over the concept itself about how to break down a program in order to make it more understandable for the machine. So we are going to use more of a Pascal-like notation in order to understand how the interpreters work. Now I'm highlighting this so that you would know that then in the next slides, what I'm using is not an actual implementation of the interpreter, so you wouldn't be confused about the notation that I'm going to use. This is just an example notation to show you how the interpreter actually works, not to do an actual implementation for an interpreter. Okay, so I want to highlight that so when you see the notation, you wouldn't be confused about what you're going to see. So what structures do we need to simulate the IBM 650? We will need a data memory to store our memory. We will need a program memory, and we will need an instruction pointer. If you remember, we said that our memory is about 2,000, and we're going to use 1,000 words for our data memory and 1,000 for the program memory. The instruction pointer is used to point out which instruction we're at now as we are moving forward in our program. So the interpreter, what the goal of the interpreter is to execute the program and execute the operation itself. So how it works. So first, it needs to read the next instruction. It wants to decode and understand what operation included in the instruction itself. And then afterwards, it needs to execute the operation itself. And after executing that operation and be done with that instruction, we will go back into step number 1, reading the instruction, decoding it, and executing it. So this is basically the structure of the interpreter and how it works. If you notice, this is an interpreter. We're going to talk about compilers later on. But as you can see, it takes one instruction at a time, executes it, and then goes to the next instruction. When you talk about compilers, you're going to find that the compilers work a little bit differently than an interpreter. I'm highlighting this now, so when we go to compilers, you wouldn't be confused about the behavior of both. So an important question would be then, where are we supposed to update the instruction pointer? Should we update the instruction pointer at step number 4 when we continue from step number 1, where we continue back to step number 1? Well, we sometimes need to jump. So if we update it, then it's going to be overwritten. So one way of making it and making sure that at least we update it correctly is we increment it in step number 1, and then we override it and need it in step number 3 when we execute the operation. So again, step number 4 is not going to work because of when we increment it, it could be the overwritten instruction, it's overwritten number because of we have a jumping operation that we just performed. So we jump to another location. So it's better that we update it, incremented in instruction in step number 1, and then we override it in step number 3 if we have a jumping operation. So we want to be able now to decode the instruction. So we fetched the instruction. We know where to update our instruction pointer. Now it's time to decode in order to execute. So decoding instruction meaning that we understand which part of the instruction which it is. So we want to be able to extract what operation we are trying to execute. We want to be able to basically, if there is a source and destination, we want to be able to extract what is our source and what is our destination. So in order to be able to extract the different parts, we can use the mod operator here. So this is an example. We want to be able to extract the destination portion of the instruction. So we're going to do a mod operation divided by 1,000, and that will extract the destination part from our instruction. After we are able to separate the different part of the instruction, after we've been able to get the operation part, now it is time to understand what operation we're trying to perform here. So in order to select the operation, one way of doing it is to have a big switch statement. where we go over and compare and see what operation we have. So if you remember that the operation consists of two parts, we have the sign and we have a number representing the operation. So if it's a plus, then there is a set of operation we can choose from. If it's a minus, then it's another set of operation that we choose from. So it's a positive or negative, there are different operations that we choose from. So if it's positive or plus, then we basically it's either move, add, multiply, or square. Or if it's a negative number or a minus sign, then the operation could be subtraction, could be division, could be square root, and so on. So we get the sign, we get the operation number, and then we go through the switch statement in order to extract and understand exactly what the operation we're trying to achieve is. So the operation themselves, all of them are divided into two different types. There are the arithmetic operations, which are straightforward. You do not need to change the IP address. You know that you just increment the instruction pointer after executing the instruction where you're at, and the next instruction to be executed will be just the next instruction. That's for the arithmetic operation. But if we have control flow operation like greater than or less than, like the F or go to and thing like that, if something related to control flow where you have to jump to another place, then in that case we have to pay attention. Then the IP address may also to be altered when we are executing that instruction. So you have to separate between the different types of operation to know exactly how to execute them and what each instruction entails. So now we understand in general how to take the instruction, break it down, execute it for our interpreter. So we understand in general how our interpreter is supposed to be work. However, we have to ask ourselves, is our language complete now, or we still need to add other stuff to the language? And in order to answer that, we have to look at the different situations that we might encounter. So if you notice so far in our instructions, in our program, we always have to insert the address of everything explicitly. So if you have a control flow or a jumping operation, we have to explicitly say jump to address 200, for example. Or if you have an operation you want to execute, like addition operation, you explicitly specify the address of the source and the address of the destination. So we are always working with explicit addresses in our code. However, what will happen if we need to insert another instruction in the program in the middle? So you write down the program, you find yourself, oh, I need to insert an instruction. There is something missing here in my program, and you want to insert the instruction in the middle. And that will actually shift everything, especially for the control flow operations that you want to execute, because you explicitly specify the address that you want to jump to. So what are you going to do? Are you going to go ahead to recalculate all the addresses again inside your program and readjust your program? Well, it could be a very tedious operation, and that can generate a lot of error. So if you remember from different programming principle, we want to remove tedious operation from the user or from the programmer. We want also remove any error-prone operation. So a solution for that is actually we can use labels for loops instead of using absolute memory addresses. So basically, we define a new operation we have, which is the -7 operation, which defines a label, okay? So it defines a new a label that we can use instead of writing down the address. And only 100 numeric labels are possible here. And that we are going to modify the control flow instructions to jump to the labels instead of jumping to a specific address. And that label will basically include the address that we have. This is not an executable instruction. It's more of going to be at the beginning, and it's not going to be, it's more of not executed similar to what other operations are going to be executed. So how do we handle the labels in the interpreter? How we can actually find where the label is and what each label maps to, what the address the label maps to. So one way of doing it is whenever we encounter a label, we just scan the whole program instructions from the beginning, trying to find the -7, and then trying to find that label and know what it maps to, which could be very slow because every single time we encounter the label, we just scan the whole program again. Another way of doing it is to actually create a label table with the absolute addresses for the label and bind the addresses for them. So basically you scan the program, you find the label, we find the -7, you find there is a label, you have a table, you take that label and you take the address that is associated with that label and you bind it to it. So you have that table. You can scan the program all at the beginning or when you're executing the program and encounter it. You can also as well, that's another way, is you add it to the table as you're moving through the program. So the way of scanning it all first and collecting it and putting it into the table, that's the way that the compilers usually do it. It's much faster and you have everything constructed from the beginning before you're doing the execution of the interpreter execution of the instruction. And that brings us to the labeling principle, which said that do not require user to know absolute numbers or addresses, and instead associate labels with number or addresses. Because again, that allows us to significantly reduce the errors that could happen in our code and reduce the problem that could appear from using regular addresses. Now that we have our labels to mark the addresses and for them to be able to jump to those addresses instead of the user having to remember them, can we extend the same idea so that we can also label our variables? Instead of having address for the variables, we could also use a label or variable name for the source and destination, for example, instead of using them as explicit. Can we also extend the same idea instead of actually using the operations to be numbers like +5, +6? Making it harder to remember, can we also extend it so that the instructions themselves, we can use labels for the instructions themselves, creating something called a symbolic pseudocode, so that make it much easier for the user to use instructions, remember what the instructions are, and instead of having to remember the numbers for the instructions. So basically, we extend the language so that to include symbols for the program instructions, for the data declarations. So basically, what we do is here in the example here, we're declaring in values of d referenced by symbol n. So basically, we are here creating a variable s that will hold a value n and will hold n values of d. So it will hold n values of d. Think about it like an array. If the n values is 1, then basically s is holding one value. If n is a large number, then basically we are creating an array, and the values inside our array would basically be holding the value of d. And the symbolic notation of the language is that we use the word var, representing that we are declaring a variable s of n values, and the values are going to be stored as d. If n is 1, there's going to be a simple variable, and if n is greater than 1, is going to be an array, and that whole array will hold the value d. So we think about it, we are initializing an array. So we're not just creating an empty array that doesn't contain a value. If remember, other languages do not require you initializing an array when you're creating it. Here, the notation that we have is we are going to initialize our array if we have the plus and minus list of these, whatever values you're picking here. And that brings us to the seventh principle, which is security principle. No program that violates the definition of the language or its own intended structure should escape detection. Now, when you think about what we have just created by creating a label, by having a part where we declare the data variables, we're making sure that our array is declared clearly and in a concise way with an explicit definition of the size of the array. If you remember, if we go back to the slide here, you're going to find that our variable s was declared with n values. So when going through the loops, now it's much easier through the interpreter. If we are looping through an array, it's much easier for the interpreter to know exactly where to stop, to know exactly where the array ends, because we have a specific size for the array being declared before. Now, also one important thing about here that the data declaration happen in a specific section of the program. It does not happen in every location of the program. So we have everything declared at the beginning of the program. We know exactly before executing the instructions where the data is going to be located, how the data looks like, what the array, the size of the array, everything is declared. So it's make it much easier for the interpreter to actually detect the errors if it's going to happen. It's making easy for the interpreter to know the boundaries, to know what variables we're using, because everything declared at the top. So making it able to follow the security principle here, that we are making sure that the program does not violate the definition of the language or structure, and it can detect any error or problem that could happen. So it's much easier for the interpreter to detect that then. One other feature we want to go ahead and add to our language is the ability to debug, because it's always very important to debug the program. So we can facilitate debugging by printing the instruction execution in order. It's executed in order. So you print like a trace for the execution itself, the execution when it's happening by the interpreter. So it makes it much easier to trace our program. So we can have, like, interpreter can include a trace flag. If trace is enabled, then print the instruction pointer and print the instruction, so you can actually know the sequence of execution. If there is an F condition and you jump to a location, you know that instruction pointer changed and that you're executing a different instruction. So when we think about it, our language now, we have more of a complete language. We have more of a symbolic pseudocode language. What it means, symbolic, again, means that instead of using instructions by zeros on 1 and 2, we're actually using a word or a symbol or a label referencing the instruction, making it much easier to read the program and read the instruction. So for example, we have here, you have we have, for example, the 1 here, +1 representing the add operation. So we can use a label add, and instead of saying +1, -1 representing the subtraction operation, we're going to use the word sub representing the subtraction operation, and so on for all the other operations. So we also have other symbols not included in other symbol that it was not very clear in the table. We have the label label to declare a label. We have var to declare a variable, s of size n. We have the end, which is a delimiter between variable, program, and input, and it is defined by minus a series of 9s. And then we have trac. It enables and disables tracing. Tracing is turned off by default. Encountering this operation toggles tracing. So these are the other commands that we have here to indicate the end or variables or labels. So now we have the complete part of the symbolic language that we have. And from that, we can have a simple program here that is much easier to read. So if you can see here, we're declaring a variable. We're declaring variable 0 of size 1, and we declare initializing it with the value 0. We are declaring another variable I of size 1 of zeros, and so on. And then we use the end word here to indicate that we have an end for the input the data part. And now that's gonna be our program part here, where we have the stop keyword to indicate the end and with stop of the execution of the program. We have the end keyword. We're using it again here to indicate the other part of the program as well. So these are the instructions to be executed. This is the unexecutable part, indicating the data that we have. So now we understand how the instructions look like, how to break down the instruction and execute it at the interpreter, and how our instructions actually evolved over time, so that we can end up with such a program that is much easier to read, much easier to follow up than writing down machine code. So I would recommend just go back, look at machine programs, machine code, look at how much harder to read and follow up, and how much easier now to read such a program in comparison to using machine language.